The problem I chose to represent as a search problem is a maze escape. Most people are familiar with mazes. You're placed at the starting point to a maze, and the maze will have walls and paths, and the goal is to find a path from the starting point to the exit. This maze can be represented as a grid where each cell is blocked by a wall or is open in certain directions. The state for the problem is going to be the current position or path in the maze, and the starting point is going to be the entrance of the maze. The actions will be to move up, down, left, or right, and the goal is to reach the exit. To represent the maze search problem as a tree, each node in the tree is going to represent a coordinate pair that's going to describe a cell in the grid. And each edge connecting those nodes are going to represent a move that we can make from one cell to another in the actual maze. With a little information about the board, we can use A** search to optimally solve for our maze problem. Given the coordinates of our goal cell and the coordinates of our current position cell, we can use the Manhattan distance as our heuristic. A** search will determine which node to expand next with an evaluation function f of n. F of n will consider the current path cost so far, and also the estimated remaining cost to the goal, which is based on our heuristic. It will also choose to expand the node in the frontier with the lowest f of n value. A** tracks frontier nodes with a priority queue ordered by their f of n value, so that even if the most promising nodes don't lead to a goal, we'll still explore the rest of the nodes, and this guarantees that if a solution exists, we'll find it and it will be optimal. I chose the maze search problem because it's easy to visualize and the game states and actions are easily definable. I also think that the problem is flexible and can be augmented in different ways. We can add different heuristics like scent trails or direct distance. It can also be transformed into a competitive game with 2 players or with a monster opponent that distracts from the optimal path. And the maze itself can also be adjusted to add costs or weights to moves, and many different algorithms can also be applied to the problem. I also think it has a lot of real world connections like navigation apps, robotics, and video games.